Hello, my name is Peter Lindemann. Welcome to Electric Motor Secrets. I've been fascinated with electric motors and generators for more than 30 years. In that time, I've studied this subject extensively. I've also built and tested hundreds of experimental models. What I'd like to share with you today are the findings of that 30-year study. But before we go into the lab and hit the books, let me give you a little bit of history. If you are under 40 years of age, you probably missed out on electric motor shop in college. That's because in the 1970s, most of the major universities in the United States closed their motor labs to make room for the new computer science departments. Since electric motor design had not changed in the last 50 years, it was reasonable to believe that it wouldn't change in the future. So there is no longer any reason to give new students hands-on experience with these machines when one semester of book study would suffice. But remarkably, in the 1990s, motor design did start changing again. Big breakthroughs came on a number of fronts. First, the cost of the super-powerful neodymium iron boron permanent magnets dropped dramatically. This made it possible to build motors that were smaller and more powerful for their size. Next, high-speed brushless electronic commutation methods were developed and perfected. This allowed the sparking commutator to be eliminated in all DC motor designs. Even the idea of superconducting wires was revived. So, electric motor efficiency was on the rise again. Today, fractional horsepower DC electric motors are approaching 95% efficiency. This is a range of performance once left only to Tesla's three-phase AC induction motors above 50 horsepower. These new motors are so small, powerful, and lightweight that they have all but taken over in the model airplane field from the little gas engines. So, what's left to do? Is there only 1 or 2 more percent efficiency left to wring out of these designs before the electric motor reaches the pinnacle of its development? Actually, the answer is no. Tremendous improvements in electric motor performance have already been proved by a number of inventors. To bring you up to speed on these developments, I'm going to focus on 3 main topics. These are 1. The true function of the back EMF in electric motors. 2. Alternatives to direct induction for the production of motor torque. And 3. Methods of recovering some of the electrical energy input. To do this, I have to lay a little bit of boring groundwork so everyone can follow along. So please bear with me if you know some of this stuff already. We'll get to the good stuff soon. The study of electric motor efficiency requires the use of a dynamometer, or something that can measure the mechanical energy output. For those of you who don't know, the dynamometer is a calibrated braking mechanism invented by a French mathematician and engineer named Gaspard de Prony in 1821. Even today, small dynamometers are still quite often referred to as a de Prony brake. So let's go into the lab, build a dynamometer, and use it to test an electric motor. Then we can see exactly what it does and why. Here's how it's done. If we want to understand how to measure the efficiency of electric motors, we have to be able to measure the mechanical output. For that, we need a dynamometer. Now, they don't build small dynamometers for small motors, so we have to build our own. So what we're going to need is a wheel of known circumference, a leather strap, 2 spring scales, a tachometer, a voltmeter, an ammeter, and a calculator. Let's see what this looks like. The first thing you need is a wheel of known circumference. In this case, we have machined this one so it's exactly 1 foot in circumference. And you need to have it to have a hole and a set screw in there so you can attach it to your motor, and every time it turns around, then we will have a calibrated length or distance that it's traveled. So the first thing you need is a wheel. The next thing you need is something to create a resistance against that wheel, and in this case we have used a thin strip of soft leather. And we've put a hole in each end of this so we can attach our spring scales to it. So the next thing you need is a small piece of soft leather. The next thing you need are 2 spring scales. And these are calibrated, calibrated spring scales that you can buy at Edmund Scientific or a number of other different kind of scientific supply stores. And these are adjustable so that you can get these to be relatively accurate. So you need 2 spring scales. The next thing you need is a tachometer, something that's going to measure how fast your motor is turning when you take the measurements of the resistance to turning it. So you're going to need a tachometer. You will also need to measure the volts and amps going into the motor so we can understand how much electricity we are using to drive the motor. So these will measure our inputs. So you need a voltmeter and an ammeter. And finally you'll need a calculator, something that we can take all of these numbers that we have taken and run them through an algebraic equation to determine the efficiency of the motor. So again, this is what you'll need. A wheel of known circumference, a piece of leather, 2 spring scales, a tachometer, a voltmeter and an ammeter, and a calculator. And from these, we can build our own dynamometer. Okay, here we are with our setup. We have the power supply driving the motor with our wheel attached, and we're going to run the dyno test. Now, what we're going to have to do this is we're going to have to take 4 measurements simultaneously. We're going to have to read the volts and the current, while we also read the RPM and the deflection on the spring scales. So here, let me show you, as we do this, what this is going to look like. Got the spring scales here. I'm going to wrap the spring scales around here. And what's happening is that you can see, maybe you can't see, but that the one in the back deflects down, whereas the other one is relieved because it's turning in that direction. So the front scale is still sitting at 0, but the back scale is reading about 600 grams deflection. And as you can see, it slows down and the current draw rises. So you can get an idea of what's happening here. You can tell that the motor is slowing down because the sound changes. You can see that the current rises. So we're going to take all of these measurements simultaneously to get an idea of the efficiency of the motor. So here's another shot of the dyno test showing that there's almost no deflection on the front spring and about 700 grams on the back. You can see how much it's pulled the back spring down and how much it's relieving. This one, it's still sitting basically at 0. Okay, so let's take some measurements and see what we get. We'll put the strap with the spring scales on, and you can see where I've got them. I'm holding them both with one hand. And I've got the tachometer here, and I'm going to shine my spot on here. And I'm going to bring the current up to 7 amps, right like that. And there's my readings, 1864, about 1868. I have a deflection on the scales of 700 grams, and there's my readings before my strap gets too hot like a burner. So you have to take all 4 measurements simultaneously, and now we can calculate. Okay, so here are the measurements we saw on the bench. Our input was 12.1 volts at 7 amps, and that comes to a total of 84.7 watts input. We know that 1 horsepower is 746 watts, so when we divide our measurement here, 84.7 watts by 746 watts per horsepower, we get that our electrical input was the equivalent of 0.1135 horsepower. Our outputs were measured as 1864 RPM and 700 grams of deflection on our spring scales. Now the first thing we have to do is convert these two quantities to what we need, and we're going to measure the horsepower mechanically in foot-pounds per second. So we have to first convert the RPM into feet per second. So we know that our wheel is 1 foot in circumference, so 1 revolution equals 1 foot. So RPM is revolutions per minute, so if we divide that by 60 seconds per minute, we get revolutions per second. And for our wheel, revolutions per second equals feet per second. So we can take our RPM, 1864, divide by 60, and get 31.06 feet per second. The second thing we must do is convert grams into pounds. 1 pound equals 454 grams. And we measured 700 grams, so when we divide that by 454 grams per pound, we get 1.54 pounds. So continuing, we take our 31.06 feet per second, multiply that times 1.54 pounds, and we get our total mechanical measured output at 47.88 foot-pounds per second. So we know that 1 horsepower equals 550 foot-pounds per second, so when we divide this, we get our total measured mechanical output at 0.087 horsepower. Efficiency equals output divided by input. So here are our outputs and inputs, and when we divide these quantities, we get this fraction 0.767. We multiply that times 100, so we get our measured efficiency of 76.7%. Not bad for a 1/10 horsepower motor test. Okay. You just saw me demonstrate the dynamometer test. You may have noticed that it is pretty hard to take all 4 measurements simultaneously by hand. Obviously, I could have gotten a more accurate measurement if the spring scales were hanging from a fixed bracket with a preset tension. Then it would be simple to speed the motor up to the point where the front spring scale read 0 and all the tension was on the back spring scale. An RPM reading could be taken with a tachometer at this point, with all the values remaining stable for accurate recording. But right now, I'm just trying to demonstrate the fundamental effects, so precision measuring is not absolutely required. If you were watching closely, you might have thought that the current reading was slightly higher than 7 amps. But for our purposes, the numbers I'm using are adequate, and our calculations are pretty close. So let's go back into the lab and explore some more of the other behaviors of our direct induction electric motor. Okay, in this experiment we have this power supply dialing up just with a 1/2 volt and a little over a 1/2 amp. And all I'm trying to do is show the polarity of the applied voltages and the speed and the generating and the motoring action. So we can clearly see that this motor is turning in this direction when we apply the proper polarity to it based on its own wiring schematic. In other words, it wants positive to the red wire and negative to the black wire, and it will turn in this direction. I'm going to disconnect this. And I'm going to hook the meter up with the exact same polarities. And I hope you can see this meter. Now I'm going to turn this in exactly the same direction as we did when we hooked it to the power supply. And what you see is it looks like it's generating a voltage in the same polarity. You see that? That this is a positive value on the meter. If I turn it in the opposite direction, immediately the minus sign comes up. Okay? So what does this mean? In other words, when I turn it in the same direction that it turns, it looks like it's generating a voltage that adds to it. But the fact is now this is acting as the source and the negative is coming out the black wire and the positive is coming out the red wire, whereas when it was hooked up to the power supply, it was exactly the opposite. The negative was going in the black wire. So actually what this shows is when I turn it in the same direction, it is actually generating in the opposite. It's generating the voltage in opposition to. It's trying to feed it back out, whereas before we were feeding it back in. So I just want you to understand that when it turns in one direction, it motors, but it generates in opposition to itself. This is another experimental setup that I've put together for this educational video. It consists of two identical permanent magnet DC electric motors. One of them will be run as an electric motor from our power supply. The other one will be run as an electric generator turned through this shaft coupler. Here's our next setup. We have the power supply, again, connected to the small drive motor. It's mechanically driving the second drive motor to be run as a generator. And then we'll be looking at the voltage generated by the second motor on this meter here. So I'm going to turn this on, and we're going to use this demonstration to explore the activities going on inside these motors. You saw in the other demonstration when we did the dynamometer test that when we mechanically loaded the motor to get our measurements, we noticed that the current reading went up. Now, many people believe, who have not studied these things, that that is caused by the back EMF. Actually, that is not what's happening. And to understand what the back EMF is doing in these motors and generators, I've set up this little demonstration. What I'm going to do is I'm going to dial up enough voltage here to run this at 4 volts. These are little 12 volt motors, and I don't want to overload them. So I'm turning this one as the motor and using 4 volts, and it's drawing about 3 amps. So this total situation here is about 12 watts. It's a low amount. And all I'm trying to do here is we're not trying to do any efficiency tests or anything else as far as power production. But I want to show you what the back EMF is and how it works. Now, the reason you can't build a self-sustaining combination of a motor and a generator using this type of equipment, this is what's called a direct induction machine. It has a permanent magnet field, and it works equally well as a motor and as a generator. So here, this one I'm using as a motor, this one I'm using as a generator, and I want to show you what's going on. Inside this one, it's working as a generator in opposition to its motoring activity. And this is what is called the back EMF. In other words, depending on how fast it's going, it's generating a voltage. And we can see that by just running this one. We're not drawing any power out of it, so we're not creating any load, but we just want to look at the voltage that it's generating. I have these two directly coupled, and they're the same exact style motor. So we can be pretty sure that if this one is generating a minus 3.18 volts at this speed, that this one is also producing 3.18 volts inside of the armature that is in opposition to the 4 volts that we are applying. Both of these machines generate voltage in direct relationship to the speed. So you can see on this meter, which is now creeping up to, as the bearings warm up and it's able to turn a little bit faster, we can see that the generated voltage is rising slightly. That's because the speed is rising slightly for the same amount of applied energy. So that's typical of these types of motors. Now what I want to show you is exactly what causes these effects to happen. Many people believe that when you load the motor, the mechanical drag is what causes it to draw more energy. But actually, what's happening is that as you load the motor, it's turning slower. As it turns slower, it generates less reverse voltage, and it then draws more current because the resistance that it's going through with less reverse voltage simply draws more current. Many of you haven't studied these things, and here's a perfectly good book called Basic Electricity. This was developed by the Navy to teach new recruits the new science of electricity and electronics in the 1950s. In the back of this book, there's a section on electric motors, and here is the page where they talk about counter-electromotive force. And you can see in this diagram here, here's a north pole, here's a south pole, and you have a winding that goes through it. And the diagram shows basically you have the resistance of the armature winding, and the counter EMF is shown as a battery, something that can generate a voltage, in opposition to the applied voltage. So you can see through the commutator brushes. So you can see that as this turns faster and faster, this counter EMF is generated, which opposes the applied voltage. This is what causes the current to drop through the fixed resistance of the armature winding. So actually, the counter EMF, or the back EMF in a motor like this, is actually what causes the current to drop to its lowest possible value when the motor is unloaded. So it's the back EMF that causes the motor to have a very, very low idle current when it's unloaded. As it's loaded, it slows down, generates less back EMF, and draws more current, which makes the motor stronger. This is a wonderful setup because it makes these motors, it makes them self-regulating. Notice if I slow it down at all, it starts drawing more current over here. I've got it up to 4 amps here, and you can see that the amount of voltage at this speed that it's generating is down to 2.85. But I let it go back up to speed, and it generates more. If I slow it down at all, it generates less counter voltage and draws more current. So this is how these motors work. This is how the back EMF works in the motor mode. So this is completely understandable, and it's standard right out of the books, as I showed in the section from Basic Electricity. Now, by calling this back EMF, it tends to obscure what it is. And what I want you to see is that the back EMF, when this thing is driving as a motor, the back EMF is really just the reverse direction generated voltage. Back EMF. EMF stands for electromotive force. So really what the back EMF here is the reverse direction generated voltage. Okay? And you can see it. The reverse direction generated voltage. And this is created simply because of the speed that this thing runs. This thing is turning as a motor because current is moving through it. But it will generate the reverse voltage simply because it's turning at a particular speed. Now when we turn this around, let's look at the generator side. If we ask this Right now there's no real current moving in this. We're just looking at the voltage that's generated. But now if we actually ask it to generate some current, okay, I'm going to ask it to light up this little light bulb a little bit. You can see that it draws more current here, and you can hear it slow down. You can hear the tone change. Okay? And as it slows down, it generates less reverse voltage. Do you understand? So here, now the current is moving in it. It's starting to motor. It's starting to motor against itself in the opposite direction. So when the machine is running as a generator, we'll call the back EMF the reverse direction motor torque. When it's running as a motor, we will call the back EMF the reverse direction generated voltage. So what you can see now is that this is exactly the same machine, and you can bias which effect you're looking for. If you actually force current through it, like from our power supply, it motors ahead, and the motoring effect gets ahead of the reverse generation. In this situation where we're mechanically forcing it to turn, the generation effects get ahead of the reverse motoring effects, and therefore it will push electricity out of the system to light external loads. But both effects are happening in both machines simultaneously. So now let's go back to the book and take a look at the symbolic representation of what we just saw on the bench. Here in our diagram, it says the illustration represents the back EMF as a battery opposing the applied voltage, with the total armature resistance shown symbolically as a single resistor. So this is a symbolic representation so that we can understand the functions going on in the circuit. And in fact, this is the exact physical arrangement of our test motor. We have a permanent magnet field on both sides of a current carrying conductor that happens to be in the slots of the armature. We have commutator sections here with brushes going out to our DC voltage supply. And as this thing spins faster and faster and faster in the field, this value of the back EMF, or what they're calling the counter EMF, becomes a larger and larger value, which opposes the input voltage. And so what we see is that the resistance of the armature winding, which may represent in our motor maybe 20 feet of magnet wire between the commutator sections, that represents a very, very small resistance. And so this represents both the resistance of the armature coil wire and the brushes. So this value is rising, and so the motor regulates up to a top speed. Now let's take a look at what the book says about this situation. So here is a blow-up of the paragraph that is directly underneath this diagram that I just showed you. And here's what it says. What actually moves the armature current through the armature coils is the difference between the voltage applied to the motor minus the counter EMF. Thus, the applied voltage minus the back EMF is the actual voltage effective in the armature, and it is this effective voltage which determines the value of the armature current. Since generally I equals E divided by R from Ohm's law, in the case of the DC motor, the applied current is equal to the applied voltage minus the back EMF over the armature resistance. Also, since according to Kirchhoff's second law, the sum of the voltage drops around any closed circuit must equal the sum of the applied voltages. Now, I must admit that I agree with absolutely everything this says. So this is how this motor works. Now, let's take a look at another analogy. So here is our simple back EMF analogy, and this is set up very similarly to what we saw from the book Basic Electricity. What we see is we have an applied voltage, and in this case we're just going to say these two 6-volt batteries give us a 12-volt supply. So that's our applied voltage. And what we're going to do to simulate our back EMF is we're just going to take another 6-volt battery here and put it in opposition to the first battery so that they have a negative common ground. And so what we see is that this point in the circuit is plus 6 volts potential, and this position is plus 12 volts potential. And then we have our little load device. In this case, it's a resistor with a little bit of light coming out of it, so we're going to call this a little 6-volt light bulb. And then here we have an amp meter with a 0 to 6 amp scale, and it's just on the first notch here, so we're going to say that there's 1 ampere moving in this circle. So by what we just read in the book, the applied voltage minus the back EMF gives us our effective voltage. So we can see very obviously that there's 6 volts running this. And since there's 1 amp here, by Ohm's law, we can calculate that the resistance here is 1/6 of an ohm. So what we see is that this thing here, our little load, is doing a number of things. First of all, the voltage here is the difference between the applied voltage and the back EMF. And the resistance here in relationship to this effective voltage here is what determines the amount of current running in the system. So the resistance here is the regulator in the system. So we can clearly see, now that we have all the values, we see 1 ampere, we see 1/6 of an ohm, we see 6 volts on the load, we see 6 volts back EMF. We can clearly see that there are 12 watts moving through the system, 12 volts times 1 ampere, and 6 watts of energy are dissipated here at our load, and 6 watts are represented here. Now, if this is a real battery, what's happening is that this 6 watts here is actually charging this battery. It's in opposition to the discharging battery, so obviously this 6 watts represents 6 watts of charging potential for energy being stored at a rate of 1 ampere. So this regulates the charge rate of our battery here. So let's now go back to our motor analogy and see how all of these things fit in. Okay, so here is our back EMF analogy again, and I've used almost the exact same drawing, except now I've plugged in the values that we saw from our back EMF demonstration in the motors, where we clearly saw that our applied voltage was 4 volts right on the power supply meter, and our current running in the system was 3 amps, again on the power supply meter. And here the back EMF we saw on the yellow meter, which was the voltage being generated by the second little motor. It was turning at the same speed as our primary driving motor. So we have all of these quantities by measurement. We have this on the meter, this on the meter, and this on the meter. So we can solve for the other two things, and so we can clearly see by the book that our applied voltage minus our back EMF creates our effective voltage. So we can clearly see that 0.8 volts was the effective voltage on the armature. And now, since we have 0.8 volts and the current, we can solve for this quantity. So again, using Ohm's law, we can see that the resistance is going to be equal to the voltage divided by the current. So 0.8 divided by 3 gives us a resistance here of 0.26 ohms. Now, this is where the books stop. And there are two fundamental corollaries here which are never mentioned in the book. So this is the first big secret about back EMF. And that is that you saw in our light bulb analogy that I just showed that we can figure out how much energy is dissipated here at this section simply by multiplying this times our current. And so what that means is that the energy dissipated in our armature winding is 0.8 volts times 3 amps, or 2.4 watts. Secondly, we can look back here at the back EMF, and we see that it is 3.2 volts. But in this case, this is just a voltage on the winding, and there's no storage mechanism involved with it. So there's no way to store this energy in opposition to our applied voltage. So what this does, what the back EMF does here, is it simply destroys 3.2 volts. And the fact is that only 0.8 volts gets through the system. So here's what we see. We see that 3.2 volts times the 3 amps, or 9.6 watts of energy, is destroyed by the back EMF, and 2.4 watts of electricity is what creates all of the mechanical energy that the motor puts out. That is the secret of this problem, that the back EMF in this case is destroying 80% of the energy that we are applying. Our 4 volts times 3 amps is 12 watts. 9.6 watts is destroyed, and 2.4 watts is what creates all of the mechanical energy the motor puts out. So, with this in mind, let's go back to our dynamometer test and see what this implication means about the efficiency of the motor. So here are some revised figures for our dynamometer test, and as you can see here on the second line, motor under load, these are the values that we saw. It was 12.1 volts, drawing 7 amps, and it had slowed the motor down to 1864 RPM. Now I went back and actually looked at what the motor was doing when it was idling, and it was drawing same 12.1 volts, but it was only drawing 1.1 amperes, and it was turning at 2235 RPM. So in order to understand what kind of back EMF this motor might have been generating at our test speed here, I went back and actually just powered up the motor in an unloaded condition and just put in enough voltage to turn it at that speed, and what it drew was 10 volts. Now we've seen in this motor, because of the voltage drop on the carbon brushes and what little resistance there is left on the armature windings, that typically the back EMF has been running approximately a volt below the applied voltage in unloaded conditions, and it was even slightly higher than this in the smaller motors running at lower voltages. But I think it's fairly safe to say, since I didn't have the complete setup to run both motors and like motors of that type, but I think it's reasonable to believe that at this speed, the back EMF generated by this motor is approximately 9 volts. So the effective voltage running our motor under our load test was, by the book, the applied voltage minus the back EMF equals the effective voltage, or 3.1 volts, was what was driving our motor forward under our load test. And so this gives us also the beginning of an understanding of the possibility of developing a coefficient of performance for these motors based on the function of the back EMF. So if we look at our effective voltage, which is what motors the motor forward, and divide that by our applied voltage, which is the what we actually have to spend to get it, we can get a sense of what a COP is, or a coefficient of performance of the motor, based on the back EMF function. And what we see is that the COP of the motor under this circumstance is 0.256. So we have to ask this question: what is the real power driving our motor during our load test? Because this gets back to what the efficiency really is. So if we look at the fact that what drove our motor forward was the difference between the applied voltage and the back EMF, so that's our effective voltage, times our current that was drawn at the time. So there's reason to believe that what drove our motor forward under our load test was 21.7 watts. Of course, we had to put in 84.7 watts to get it, but this is what drove the motor forward. Now, if we look at converting that again to horsepower, 21.7 watts divided by 746. So our real input was 0.029 horsepower. If we plug that into our efficiency equation, what we come up with is that the motor is actually 300% efficient at providing mechanical energy production from effective input. So, and this is by the book. So, if we look at the real efficiency, which is 300%, and we multiply that back by the effect of our back EMF, which is the 0.256 COP, then we come right back to the original number that we calculated during the first calculation of our dynamometer test, which is 76.7% efficiency. So there is at least reason to believe, not only in the numbers but on the bench, that we must draw this conclusion that the back EMF in the system masks the excellent performance of the motor and is actually in the process of hiding it behind a very low COP. Now this also leads to a clear understanding of exactly why most dynamometer tests for induction motors of this type, it is recommended that you slow the motor down to 1/2 of its idle speed to take the measurement. And now we can see why this is such a good idea, because it raises the COP to about twice what we saw here. In other words, if the back EMF is dropped by 50%, then we can get a lot more effective power creating mechanical energy. And with the COP up to 0.5, then these numbers can quite often get up into the upper 80s and maybe even low 90s for a little motor like this. It's not uncommon. So here we have a very interesting situation which tells us something very important about the back EMF and what its function is in the motor. Okay, now before we get all goofy and think that off-the-shelf electric motors are producing 300% efficiency, let's get away from our analogies and our symbologies and our representations and get back to the back EMF reality. And the reality is, and I've got this drawing here set up to have the values that we just saw in the dynamometer test again. So we have an applied voltage here of 12.1 volts. Our amp meter now is reading 7 amps. And here's our little brush commutator sections. And here is our inductor. And we can see that Both the forward and the backward EMFs are distributed evenly throughout the inductor. So these aren't a series event as we saw in the analogy drawings. So in the analogy drawings it was obvious that these were separate events. But here they are concurrent events in the machine. And so they can't be separated because they're actually happening on the same component. In other words, when current moves through this winding in the magnetic field, it produces a mechanical action which motors the motor forward. When that happens, it actually starts moving these coils through the magnetic field, and that generating action generates our back voltage. So what we see is that both the motoring and the generating effects look like mirror images of each other. And they're quite often taught to be mirror images of each other. But actually they aren't. They aren't mirror images of each other. And this is very important to see. In fact, they are actually reciprocals of each other. And we saw this on the bench. We saw that when the back EMF was the highest, the motoring effect was the weakest. It might have been the fastest, but it was also the weakest. So the mechanical energy production was the weakest when the back generated voltage was the highest. As we started slowing the motor down, the back EMF dropped and the motor torque rose into the load. So the mechanical energy production was getting stronger as the back EMF was getting smaller. So you can see that they aren't mirror images of each other, they are reciprocals of each other. And this tells us that they are not the same thing. They are happening in the same component, in the same location in the motor, at the same time. And that is why they cannot be separated from each other in this configuration of motor. The only thing keeping them from being separated in this situation is the geometry of the motor. So, there's two things that I want to bring to your attention. The first is, and this is an ordinary electric motor, when we put electricity in, this applied electrical voltage and electric current do two things. And that is, they produce a mechanical energy manifestation out as torque on the shaft, and it generates electricity. It does two things. It produces mechanical energy output, and it produces an electrical energy manifestation. In this case, the electricity is applied against our input and subtracts from it. Now, the question is it possible to create an electric motor that takes advantage of all of these things? In other words, we put electricity in, we're going to get mechanical energy out, and we're going to get electricity produced. And is it possible to create a geometry of machine that will allow this electricity to come out as a positive quantity and not act against our applied voltage? And the answer is yes. This is possible. But we can't do it with this geometry of machine. We have to look for something else. Now this is a repulsion motor. In other words, when current is applied to this coil, it creates a pushing action against the magnetic field. And it's very strong right in the middle of the field, and it pushes its way out of the field. And what we're going to look at is the opposite situation. We're going to look at an attraction process because it's in the opposite process, not a repulsion motor, but we're going to look at an attraction motor and see if this won't allow us to separate these effects and create a much more interesting result. This is the cover of the 1940 edition of The Boy Electrician by Alfred P. Morgan. And this book was a hands-on book for young boys who were learning about the new science of electricity. It is filled with a wide variety of model building exercises and so on. And what I wanted to do is I wanted to show you an electric motor from this book. So here are pages 308 and 309 from The Boy Electrician. And on these pages it begins a project on how to build an electric engine. And what I'd like to do is I'd like to read to you from this page right here, and I'll give you a blow-up shot of that next. So here's what it says. An electric engine is really a form of electric motor, but differs from the most common form of motor in that the armature, instead of revolving, moves back and forth, like the piston of a steam or gasoline engine. Electric engines are not as efficient as electric motors from the standpoint of the amount of power derived in proportion to the current used, but they make very interesting models. Various forms of electric engine were made before the first practical electric motor was invented. They amounted to little more than curiosities and could only be used where the expense of electric current was not to be regarded. So let's take a close look at this dinosaur from the past and see if there isn't anything here that's usable. First of all, we have a situation where we have two coils, one here, and each one of them has an iron core, and then there is an iron keeper that comes around. This is a pivot point right here, and this is an iron member. And then this is, of course, connected off to a crankshaft, and that's connected to a flywheel. And behind the flywheel, which is not shown, is a small commutator which allows us to turn these coils on and off at the right time. So the way it works is this, is that when the iron member is as far away as possible from this coil would be turned on by the commutator, and it would attract this iron bar over so that it would push on the crank and turn the crank. As soon as it got as close as it possibly could be to this one, it would shut off, and then this one would turn on and attract it back. So you get 2 power strokes per revolution, and it consists of a situation where there's only one magnetic field on at any given time, and it's simply attracting a piece of iron. And because this situation does not have 2 magnetic fields which are interacting with each other, this situation does not generate any current by induction. So in that sense, this little arrangement, as terrible, as inefficient, and as barbaric as it may seem, does allow you to make a motoring mechanical energy torque with no back EMF. So this is at least the beginning of the understanding of the topology that we're looking for, and that is we're just going to turn one electromagnet on, attract a piece of iron, and turn it off, and let it move away then. And that is the topology of building a no back EMF motor. So let's look a little deeper into this and see if we can't find anybody who has taken this beyond the toy stage. So here is a photograph of a model of an electromagnetic engine that was designed and built in 1840, a full 100 years before the Boy Electrician reported on it. And this is essentially the same design as they showed. It shows 2 U-shaped electromagnets, one behind, and then there's a pivot point here and a bar of iron going across, and this is connected to a crank, which is connected to a flywheel. And there's also a commutator system behind. And so what happens is that you can see on the bar on the back, as soon as it's at the highest level like this, the back magnet would come on and attract that piece of iron down. And you can see they're using as a small and as short a stroke as possible, because what they early found out was that the magnetic field only produced extremely strong forces at extremely close distance. So one of the problems with this type of arrangement was that when the forces, the magnetic forces pulling this down, were at their strongest, you were basically at the top dead center or bottom dead center of the crank, which is the place on the crank where you had the least efficiency of energy transfer. In other words, all of your forces were being pulled perpendicular to the shaft, and they weren't being applied tangential to the shaft. You need forces that are going to apply force tangential to the wheel to transfer the energy efficiently. And so what you can see in this geometry here is that when the force gets very strong, it's really just creating a force that's pulling down on the shaft and not actually applying rotational force. And this has been the problem with these systems from day one. Here's an early rotary design by Charles Wheatstone, the gentleman who figured out how to measure resistors using the Wheatstone bridge. But here we have a fixed ring of electromagnets, and these are each stationary. And then we have mounted on a shaft a ring of iron which is mounted eccentrically. As you can see, it's closer to these than it is to these. And so what happens is that when it's just when the ring is just approaching, like this one here, it would turn, this magnet would turn on, and it would rotate the ring around to the point where it would be the closest again. But again, when the gap was largest and the forces were attenuated dramatically because of the air gap, you could get a fair tangential force to draw it in. But as soon as the forces started getting strong in here, in other words, when we get to like this position here, if this magnet was still on, all it could do is, if it just stayed on, it would just come around to this position and lock in place, because all of the force then becomes radial, perpendicular to the shaft. And again, in spite of the fact that this doesn't have crankshafts and other things like this, it still suffers from the same problem, that you turn the magnet on when there's a huge air gap, when the forces are the weakest, and that's when you can get a tangential force. And as soon as the gap gets smaller and smaller and smaller and the force gets very, very large, what happens is that it rotates out from being tangential to being perpendicular. And so this motor had the same exact problems as the linear ones that were cranked off to a crankshaft. Well, literally hundreds of topologies were tried, and no one seemed to be able to figure out how to make this type of situation work. Here's a patent from 1885, and this inventor has finally said, okay, this effect is essentially a toy, and so what we're going to do is we're going to just put a doll on a swing and with a little iron bar here, and we're going to put a little bit of a commutator up in the top of the swing here. And so every time the doll gets very close to these, we're going to turn it on just for a very short, brief moment, and it will cause the doll to swing back and forth and back and forth and back and forth. And here is actually a working model of the original device from 1885. And many people came to this conclusion and tried to take it no further. So there were a few intrepid inventors and motor designers that refused to give up on this method of just attracting a piece of iron into a magnetic field. And here's a patent from 1920 showing 3 electromagnets, and basically this is an iron piece which is slidable along this axis, and then there's a crankshaft here. And so this begins to show a topology which has been generally referred to as a solenoid engine, because basically what he's got here are 3 electric solenoids, and this is the iron keeper in here, and it goes all the way to here, all the way past halfway down and around. And so what he wants to do here, because all of the lines of force are going to be in here, so he's concentrated the lines of force in a very, very short range, and there's a very, very small air gap on this edge here, and so all it has to do is when this coil turns on, this iron piece is drawn up into there to complete the magnetic circuit and to displace the air. Now again, you can see when the iron piece is all the way extended, as it is in this situation, the force at the end of this stroke should be fairly considerable. And since one of these is going to be pulling all the time, at least one of them will be pulling all the time, this motor probably had a fair amount of mechanical energy. And so there were ways of starting to work with these ideas that people continued to work with throughout this entire period. So here we have another patent from 1936. And here we see the radial solenoid engine taken to its maximum development. And so here we have actually 12 solenoids all the way around, and these, so this is the master cylinder and master crank, and then all of the slaves on that radial section are attached to it. And we can see from the commutator symbology here that he has about 3 of these solenoids pulling at any given time. So approximately 1/4 of the cylinders are pulling all the time, and the others are resetting. And actually, if I go out a little bit, you can see in the bottom here that he's actually planning to have 3 rows of this radial arrangement at 120-degree offsets, which you can see here in the crank. So here's the main crank for the one that we're looking at, but then there's a main crank for the next row and a main crank for the next row. And so what we're looking at here is obviously not a toy design. This is designed for the production of real power. And so it proves that not everybody had relegated the idea of the magnetic attraction engine, or in this case, the electric solenoid engine, to obscurity. There were people who believed that this held a promise that other motor designs didn't hold, and people worked on it throughout this entire period. Now, I probably never would have taken the electric solenoid engine seriously had I not run into this man. This is the work of Benjamin Robert Thiel, generally known as Bob Thiel. And this patent, which issued in 1978, again looks like the kind of radial design that we've seen in the earlier models. And he's got a master piston here and 3 slaves. And he actually has 2 of these next to each other, so this becomes an 8-cylinder engine. And but unlike the other motors, the claims that were made for this motor were really, really quite extraordinary. And what I'd like to do is show you some of that right now. Now here's a close-up shot of Bob Thiel in mid-1970s in front of one of his 8-cylinder radial solenoid engines, electric solenoid engines, which he called the magnipulsion engine. And let me just, this is the cover of a piece of company literature from his company called the Magnetile Industries. And on the bottom here he has this quote from Voltaire. And it says, "There is nothing as powerful as an idea whose time has come." So let's go into the company literature of the Magnetile Industries Incorporated and find out about Bob Thiel's magnipulsion engine, what he calls tomorrow's energy today. Now, one section of this document from Magnetile Industries is presented as a question and answer session. And so what I would like to do is pull a few brief excerpts from this section of the document and bring them to your attention. And the first question here in this section is, what is the magnipulsion engine? And the answer is, an engine that is motivated by electromagnets which serve in a manner similar to pistons in an internal combustion engine. It receives its initial power from a car battery. There is a continuous charge of energy without any supplementary source other than the battery. The capabilities of the magnipulsion engine are relatively unlimited. We know it can power automobiles, air conditioners, home power plants, machinery, or anything which utilizes fossil fuels or electric motor drives. And here's question 2. Why hasn't this inexpensive, practical, and powerful energy concept been discovered before this? The answer is, the field of magnetics has not been explored comprehensively by the scientific community. What has been done in this field before the arrival of the magnipulsion engine has been spasmodic. To the inventor of magnipulsion, these forerunners missed the mark considerably by not harnessing the principles now patented in the magnipulsion engine. So here we have direct statements which basically say that he seems to have found the secret, the way of getting the power out of this arrangement of just attracting a piece of iron into an electric coil. He is claiming to have figured it out. And he's also claiming that the amount of energy that comes out of it will not only run the motor, but apparently keep the initial battery charged. So, let's see what else Bob Thiel says. And here, question number 7. How does magnipulsion compare to current standard engine concepts? The magnipulsion engine may be described as superior to any other engine concept known to the inventor, including the present internal combustion engine and electrical engines. And again, here is question 15. Can I bring my engineers to discuss business with your company? The answer is yes. Prospective buyers and their engineering staff are welcome. But they must be prepared to see and learn of a new and revolutionary discovery which some in the scientific community consider contrary to established laws of physics and or electrodynamics. And here is question 24. What is the main difference between magnepulsion and other engines which use electricity to power machinery, etc.? The answer, unlike electrical motors, which take a continuous supply of electric power, the magnepulsion engine runs continuously on relatively minute quantities of pulsating current. Here's a couple pictures of some of the working models. And then questions 29, 30, and 31. Does the engine emit any pollution? No, the engine is pollution-free. Is there any noise to the engine when in operation? Negligible. And here's the big bad heresy. Is there any reason to believe that the magnepulsion engine is incapable of taking over for the internal combustion engine and present electrically powered motors? And here's the answer. The principle proving the utilization of energy from magnets has been fully and completely proven in our shop. Magnepulsion is convertible into relatively unlimited horsepower and therefore can be used wherever these other power sources are currently used. So here are some photographs of some of the working models. This was one of the original 4-cylinder units from his first patent. Here is an 8-cylinder unit from the second patent, and so on. Let me just give you a quick close-up here of some of these models. So he had multiple working models of a very extraordinary a magnetic attraction solenoid engine. So here is the diagram from his second patent showing the 4-cylinder radial construction. And so we see that he has 4 electric solenoids, and this is the master piston here and the master crank, and so the other slaves are connected to it. And what we see is that when the crankshaft is at top dead center, the movable plunger is completely inside the coil. And then when the crank is at bottom dead center, which is what it is for this one, it looks like the movable plunger is approximately 50% withdrawn from the system to see what it would do. Okay, here's an example of the kind of motor we just saw from the Boy Electrician. This is a magnetic attraction motor, and in the form of, we have a coil here that has 4 windings on it, and as you can see, I can stick my finger down here. It has a hollow core, and underneath here, this is a piece of iron, and it's attached to this crankshaft. And what happens is you turn the coil on, and it draws the magnetic field in here, draws the piece of iron up to it, and then the commutator on the back turns it off, and then the iron can fall out unopposed. So that's the motoring cycle. So the coil turns on here, it sucks it up, turns off here, and it lets it drop out. Electrically, when the coil turns on, it draws power from the power supply, and when it turns off, the circuit allows the discharge of the magnetic field to create an inductive collapse, and that energy is siphoned back through a secondary circuit to charge this battery in the back. So we can not only we can take electricity from here, create mechanical energy here, and get electricity back over here. And that all we have to do is stagger these events in time to so that they don't oppose each other at any given time. So let's see how it works. So I've got the power supply dialed up to about 12 volts, and you can see that the current is jumping around because this samples faster than this is turning on and off. Well, you can see that we've already pushed our battery up from where it was before, and it continues to climb. Now, the amount of energy that this draws is specifically related just to the resistance of the wire in the coil and the duty cycle of the commutator. So no matter how fast or slow this turns, it's going to draw exactly the same amount of energy. Now, there's a number of things that determine how much mechanical force is produced, and primarily it has to do with the efficiency of the magnetic circuit. Right now, this is in its absolutely worst condition because the magnetic field is wide open to the environment. But it still is enough to draw the piece of iron in. Now, what we've done is we've built this little iron keeper here. This is just to get it. We can put this directly around the coil, and this is just some plastic pieces that we filled up with iron filings and glued together, so that we can stick this down here and start folding this magnetic field down around itself so we can get a better magnetic circuit going. This is just a piece of junk that we pulled off the shelf, but it has some iron here, and as soon as I put this on the top and really start folding this magnetic field down, you can see that it speeds way up. Now, what this means is that the coil is turning off more often, many more times per second. The faster this goes, the more times the coil turns off per second, and so it charges the battery faster, even though we're still not drawing any more from over here. And now you can see that at this speed, we can see that the current has really settled down to about 2.3, 2.4 amperes, and that's what the system draws to run the motor. Now, what I'd like to do is, and we're pushing the battery up to 13 volts. Now, this battery is fairly well charged, so it's not too difficult to push it up here because this battery is almost fully charged as it is, but this illustrates the point. Now, the other thing I want to show you is you can see that the current basically is centering right around 2.3. And if I raise the voltage just a little bit and make it go a little bit faster, then we can get it to stabilize at, say, about 2.3, 2.4, and so that's where the current is. Now, we saw with the other motors, the minute that I would try and slow this down at all, then the current that it was drawing would jump up completely. But now on this motor, if I slow it down, you see that the number doesn't just go up, it also goes down, so it's still jumping in the same range, and again we're into that sampling problem again. But basically what happens is that the duty cycle of the resistance of the resistance of the coil stays the same, and the duty cycle of the commutator stays the same because it's on the same amount of time, same percentage of time, whether it's going fast or slow. So the total amount of current is determined by those two factors and those two factors alone, and not in relationship to what the mechanical load is. So here we have a much more interesting motor that shows the principles that I was talking about when we were looking at the standard motors. Here we have a way of taking electricity, creating a motor torque, and getting some of the electricity back in a way that doesn't generate electricity against itself and cause a reverse motoring effect that slows the motor down or makes the motor draw more current when we mechanically load it. Now what I'm going to do next is I've got this little belt, and I'm going to attach this belt to our flywheel over here and attach it to this little permanent magnet DC generator over here. So I'm going to start driving this as a generator from our motor. Okay, and so I'm going to do that. Okay, and so I've got this at about 16. Maybe I'll crank it up a little bit more. And then I want to show you, so I've got this running at about 17 volts, and as you can see, the current it's drawing is right around 3.3. But now what I can do is, and now see we're turning it off and on so often that it's really starting to push this battery. But now what I can do is I can ask this generator to run a load. And as you can see, it slows it down, actually acts to do work, but the total amount of current that is drawn from the power supply stays basically in the same range. It stays centered in the same range. So again, it doesn't immediately jump to twice or anything else. And so this is a perfectly good demonstration that shows that it is possible to build an electric motor that creates mechanical energy, gives you some of the electricity back, and operates with no back EMF in the sense that as a motor, it's only a motor. Now the reason this doesn't draw more energy when it's drawing a load is that, one, it doesn't act as a generator. I can twist this all day and all night, and it doesn't generate anything. Okay, it generates over here, but this process of moving an iron shaft in and out of a coil will never generate any electricity. So this is only an electric motor, and it is not a generator in reverse. So the fact is that the only thing determining how much energy this device will draw is the resistance of the coil and the duty cycle of the commutator. It has nothing whatever to do with how much mechanical energy I can harvest from here. It's completely out of the equation, okay? Now this motor is not particularly efficient, and one of the main reasons, you could see that when I put the topper on here, it started going a lot faster without drawing any more electricity, and shows you that the amount of mechanical energy I can get out of this is really somewhat independent of the amount of electricity that it draws. Now, we're probably missing out on about 50% of the mechanical energy that this thing could produce, because when we built this originally, you can see that we glued the coil directly down to this piece of plastic. So there's no way to finish folding the magnetic field down around the bottom of the coil so that we can really tightly wrap this magnetic field all the way around so that it's very, very efficient. We could probably get 50 to 60% more mechanical energy out of this for the exact same amount of electricity burned if we were able to do that with this model. So again, this shows a number of very important aspects to this, but again, this particular model has problems which can be corrected by an adjustment in the design. So here we have excellent evidence that the motors that we were looking at originally, the kind you can buy off the shelf, and that they are behaving the way they're behaving because of the geometry of the parts. And this one clearly shows that. And in fact, all motors and generators behave the way they behave because of the geometry of their component parts, and not because they're limited by some, definite need to follow the laws of thermodynamics or anything else. Each one of these devices is specifically designed to behave in a particular window, and that's what they do. And they do that because of the geometry of the materials as they were designed into the motor design itself. So here is a close-up of one of the sections of Thiel's 8-cylinder solenoid engine. And you can see that this has essentially the same construction of the machine we just tested on the bench. You can see it's sideways, and ours was vertical, but that's a minor consideration. So you saw that our moving member would move about 50% outside of the coil at the downstroke, and it was on a crank, and it would pull all the way up to the top. And we saw a number of things. First of all, we saw that, of course, it worked with no back EMF. In other words, when we mechanically loaded it, it didn't draw more current or generate any energies against itself. And we also saw, for the first time, that the electricity part of the event that could come back out of it was now not being reapplied against the input, but now, because it was happening at a different time and under a different set of circumstances, then it could also be shunted forward by reversing the circuit with some diodes, and we could actually recover that energy for a second useful output. So here is evidence that our initial analysis of the back EMF problem can actually be re-engineered, and that we saw that this machine had an electrical input but also had a mechanical output and an electrical output, both of which were working now for the first time in the positive direction, and none of these events were working against each other. One of the things we saw in our working model was that we could recover some of the electrical energy. And certainly if Teal was recovering some of his electrical energy, then that would make his motor more efficient. So let's take a look at the circuit that he used to power this machine. Now we saw in the question and answer period where Teal says that he is running this engine on extremely short duration current pulses. So I wanted to show you the commutator section from the first patent, and this is figure 6. These are the commutator wheels, and he's using a very simple arrangement of looks like just contactors. And you can see if this is the wheel here, he's just got this little nub right here, and it's going to push when it goes by, it's going to push on this mechanical contactor and just make a very, very short duration contact to turn on his coils. So this is the commutator section for one of the 4-cylinder systems. And let's take a look at the full circuit. So here we see a blow-up of figure 5, which is essentially the circuit that he discloses that runs the machine. So like he says, he runs from a battery. And this device here is a rheostat, something just to control the current. It's got a little amp meter here. And then he shows 4 parallel arrangements. And so these coils would be the solenoid, the coils and the solenoids. And then this contactor here, 61, is repeated here. So here is the mechanical contactor he shows in each one of these things. And then there is a bypassing circuit around the commutator, which looks like a standard type of snubber type of arrangement consisting of a capacitor and a resistor. So this circuit is obviously able to do 2 things. He can dial up as much current as he wants for the coils, so he can throttle the engine. And he can also basically suppress the sparking that would normally show up at these contactors using these little snubbers. But beyond that, it doesn't look like there's anything remarkable about this circuit, and it doesn't appear that, at first glance at least, that there is any mechanism to recover any of the energy from the collapsing inductors when they're turned off. So in order to understand this type of circuit a little bit better, let's dig up a little more history on this type of circuit. Now here is a patent from 1974, and it was issued to Roger Andrews, and it's called Novelty Electric Motor. And this is the basis of many of the very successfully marketed executive desktop novelties from the 1970s and 1980s. So what I'd like to do is give you a close-up of this very interesting circuit. So here is the cute little masterpiece of Roger Andrews. And this shows in the drawings, Figure 1 and Figure 6, two of the most successfully marketed versions of this toy. And we can look at this one in particular. This consists of a plexiglass kind of rail like this, and this wheel has a number of magnets on it and a very small shaft. And it will roll back and forth and back and forth. And this was very successfully marketed as an executive desktop novelty called the Space Wheel. And what I'd like to show you is this little circuit. The one above was presented as a little table that had a top that would spin on it. And what was novel about this is that you'd start spinning this. You could start to spin this top, and it would spin for 8 months on this little thing. And it looked like a perpetual motion machine almost. It would just spin and spin and spin and spin and spin. And the circuit, and of course this would rock back and forth for literally 7 or 8 months on a battery. And he was just using a 9-volt little radio battery to run these things. And essentially, if we look in Figure 1, we can see that the circuit consists of a battery, and a single transistor, and an inductor with a split winding. And that's the whole circuit. And how this operates is that there are magnets in the wheel, or in the top. This is the version that has the top. And the table was sloped down and had a low point here, which was in a ring, and then a slight rise in the center, and then rise out to the center, to the other edge. And this was a circular table. And so the top was free to kind of move around anywhere, but its preferred location would be right here in this low dip. And what that would do is it would put one of the magnets periodically right over the central inductor. And what would happen is that when the magnet would go by, it would induce a small current in this coil, and that would place the proper inductive polarity on this transistor and turn it on for a brief moment. At which point, current would be conducted from the battery through the coil. It would reverse the polarity of the magnetic field in the inductor, give a little bit of a kick to the top to keep it spinning, and then that reversal would also reverse the conditions on the base of the transistor, so that would turn the transistor off, so then the current would stop flowing and the magnetic field would collapse and generate a little bit of a back pulse. And of course, with this transistor off, there was really nowhere for this energy to go. The only other component that it was connected to was the battery. And so what would happen is there was a fairly long relaxation time between pulses as far as duty cycle goes. The on time for the duty cycle of this was probably maybe 5 or 10%. And so there was a fairly long period between the back pulse and the next forward pulse when the transistor turned on again when the magnet came around. So let's take a look at the claims made for this very interesting design. Now, normally I would dissect a patent for extreme minutia, but in this case, the opening sentence has everything we need to know. And it says, "This invention relates to electric motors, and more particularly to a novelty electric motor which appears to have no source of power." Now, certainly, in a country where patenting a perpetual motion machine is essentially illegal, This is about as provocative a statement as any inventor would dare make. And the fact is that Roger Andrews makes this statement for one simple reason, and that is that when you do the math, when you figure out how many amp hours of energy are in the battery, and you figure out how many pulses it puts out from the inductor to drive the little top around the table for 6 to 8 months, what you find is that the toy runs for somewhere between 2 and 3 times longer than it should. In other words, it appears that something is being kicked back to the battery because the battery just lasts a ridiculously long period of time, something that is way beyond anything that could be understood. So, the other thing I'd like to show you is this. So here for figure 10 we see that this is also a very, very good circuit for driving a little pendulum, so it's good for clocks and things like this. But here, figure 11. Figure 11. Now all of a sudden, this isn't a toy. He's showing that this can be made into a motor that can drive a generator and all kinds of things, and that this has implications for power production that are really soft-pedaled in the patent. Now, Roger Andrews' simple circuit relates to a family of circuits that are similar to it. And one of the most similar is the standard DC to DC step-up converter. We see that it has a single inductor and a single transistor. And the supply here could be a battery or anything else. But in this case, instead of being triggered by a magnet going by, this is just triggered by some sort of pulse train. And instead of trying to kick the energy back to the initiating battery, what this is trying to do is actually build a charge to a higher voltage over here. So just by setting the circuit up in this way with a single extra diode, then the voltage can be multiplied from our initiating source. So this is another very simple one transistor, one inductor circuit which has energy kickback similarities to Roger Andrews. Now certainly no one has done more work on this simple little phenomena of charging an inductor, getting a little bit of motor torque out of it, and capturing the inductive collapse than John Bedini. This is the cover page of his 2003 patent for what he calls the monopole motor. And let me show you that schematic right now. So here is the design of what John calls the monopole motor. And he calls it the monopole motor because on the wheel here, that is the motoring member, only North Pole magnets face outward. And so this inductor is only being subjected to North Pole magnets, and the souths are kind of inside the wheel here, and they never interact with the inductor. So here we see that all of the functions are separated and distinct, so we can see the full action of this simple type of arrangement that was at least partially embodied in Roger Andrews' executive desktop novelty. We see a battery, and we see a number of coils on the inductor, and in this case there's 3 separate coils, and they're all wound tightly together in what's called a trifilar winding. So there's very tight induction between the windings themselves. We have a movable wheel here. Andrews used either a top or a little pendulum or something else, but John says, no, this is just a wheel that has magnets on it and can be looked upon as a motor. And so what happens is that the magnet will come by here and magnetize the core. And when it starts leaving, what it does is it induces a signal in this trigger winding, which turns this transistor on here. When that happens, the battery conducts current through the coil, through the transistor, and back. That same simple inductor transistor battery arrangement. And in this case, it reverses the magnetism in here and further kicks the magnet out. So in this sense, it works just like Andrew's silly little novelty. But now there's a whole provision here to capture the energy when the magnetic field in here shuts off. And so here we have a third coil connected across a full wave bridge rectifier to charge this little capacitor. The idea ultimately is to charge this battery, and so when this capacitor gets up to a certain voltage above the battery, then a little, some sort of little timing mechanism, this is shown as a commutator in brushes, will drop the contents of the capacitor onto this battery. So this battery charges, the motor motors, and this battery runs the situation. So here we see the beginnings of an understanding of what we thought might be possible when we saw how an ordinary motor works. In other words, there's an electrical input, there's a mechanical output, but there's also an electrical output. And now here we see the topology where all of these things are working as stated, all in the forward direction, so that we can really understand these things very clearly. So here we have a simple diagram where we show all four of these ideas right next to each other. First, over here we have Roger Andrews' simple little toy motor where a magnet comes by, causes an induction, turns on a transistor, and it produces a pulse back out. And somehow some of this energy, even though there doesn't seem to be a current loop here when this is off, some of this energy seems to be forced back into the battery to make it last a very long time. Down here we have the DC to DC converter, and here we clearly show that the battery is charging and discharging an inductor, and we have some sort of little pulse train turning our transistor on and off, and then the current is all shunted over and charges this capacitor here. So again, these things are getting very, very efficient. You can buy little chips now that operate in the 93-94% efficiency for little circuit boards and things for DC to DC step-up situations. And this is a boost converter. Here we have John Bedini's basic circuit. This is the circuit that's been all over the internet for quite a long time. And this is what would be called the simplified schoolgirl motor patent. And again, showing the very extreme similarity to a simple DC to DC converter. Got the battery charging an inductor, turning on and off. You've got a winding that shows some sort of feedback mechanism when the mechanical trigger comes by. And then instead of having a common ground between the supply and the eventual collected energy, he shows a split situation so that basically this battery and this battery are not in parallel, they're actually in series. And so what happens is that this, over here in the DC to DC converter, this draws power all the time. So whether this is charging the inductor or discharging the inductor, current is coming out of this system all the time. Whereas in this situation, it acts more like a bucket and dipper system, where a charge will come out of this battery, it will charge this inductor, and when this shuts off, that ends the current loop with the charging battery, and then this becomes the source, and it discharges into this battery. So it basically it scoops some energy out of here, invests it in creating the magnetic field. That magnetic field then can do work on the wheel, and then when this turns off, this discharges and is as much of it as can be recovered and is put into the second battery. So now let's take a look at Bob Thiele's circuit and see if any of these types of activities could be going on, and it looks like they could. Here he has his basic mechanical contactor as a commutator here, and so when this is shut, the solenoid will not only act as a snubber arrangement to suppress sparking here, but it can also act as a small storage system that can transfer energy in an AC pulse. So if this charges up to many times higher than the battery, and then so if this is positive and this is negative, then this is going to be the negative side of the capacitor, and this is going to be the positive side of the capacitor. So this side of the capacitor rises to many, many times the battery voltage. And so it's possible to transfer a pulse of current in the charging direction back to this battery using this circuit. So it is possible when this system turns off that this system can kick back some of the energy back to the battery to make his battery last a very long time. So this may be one of the things that Bob Thiele was doing to make his motor perform with the superlative performance characteristics which he was describing. Now we saw on the bench that you could get a certain amount of the electrical energy back out of the machine. But to get up to the level of performance that Bob Thiele's talking about here, we probably have to look very carefully at his solenoid design as well. Because we saw that the more you folded the magnetic energy down into a closed path around the movable member, the more mechanical energy it produced without having to put any more electricity in. And we saw that on the bench. So let's suppose and let's imagine that Thiele figured out how to maximize this process, and that is a very, very important aspect of why his solenoid engines worked so much better than anything else anyone else has ever reported. So here is a close-up shot of one of the four-cylinder machines, and we see here the solenoid, and we can see a couple of things. One, we can see that the movable plunger comes out essentially or up to the top at the end of the stroke. We can see that the coil is completely enclosed in a magnetic keeper, and that the dimension across the keeper to the movable plunger, it looks like the movable plunger is approximately 1/3 the diameter of the total solenoid. So let's take a look at some other photographic evidence. So here's a side shot of the 8-cylinder magnepulsion engine model. And if we just zoom right in here, we can see that we can look down the throat of these little solenoids here, and we can also see a side view, and we can see the crank system here. And what we see is that it doesn't look like that these are built on the design from the second patent. And in fact, it doesn't look like that they are that the movable member ever comes out of the structure at all, that this is just the connecting rod in any of the positions. And again, we see that the magnetic keeper looks like it's about 2/3 of the diameter, and the movable plunger is about 1/3 of the diameter. So this suggests that the design that we tried in our motor, based on the drawings from the second patent, really weren't what he was doing. So let's go back to the first patent, because in the first patent there's another drawing that shows a different construction. So here is figure 5 from the first patent, and this looks a little bit closer to what we were seeing in the photographic evidence. The main discrepancy is it doesn't show an open top here, but for the most part it does show that the movable plunger kind of stays within the structure, and that up at the top here, when the throw is all the way to the top, then the connecting arm would be rather deep inside the structure. So let's take a look at one other drawing as part of the first patent. So here are figures 1 and 2 from the first patent, and what I'd like to show you here is if we come in on a real tight shot, we can see that the solenoid design here is much more similar to the drawings that I just showed you and the actual physical photographic evidence which the pictures of the working model shows. So basically what we have here is a solenoid piece that stays deep within the structure for its entire movement. And so now what we need to do is we need to understand how he gets these solenoids to create so much physical mechanical energy. So let's take a look at the probable internal design of this system. Now we know from the earliest reports of people trying to develop a magnetic attraction engine that the magnetic force only creates a very large physical force when the air gap is the smallest. And the best and the brightest motor designers of the last 170 years or so struggled with getting the topology right. We're quite clear that Bob Thiel figured this out, and here is essentially the essence of what he found. By essentially adding this little extra lip at the top of the keeper here, what we see is that we can turn the coil on at this point. This is the midpoint, the point at which you're at the midpoint on the crankshaft. In other words, where you can apply the most direct tangential force to the crank. And when we turn the coil on at this point, essentially the magnetic keeper is already completely made. In other words, the magnetic field can act at the closest possible range. And this means that the force on our movable plunger here is going to be maximum right from the start. But because there is slightly less iron down at the end here and slightly more iron up here, moving upwards will allow for the creation of an even more advantageous magnetic circuit. And so that is the direction of the force generated. So let me just back out here and let's just take a look at the entire design of the magnipulsion solenoid. So we saw from the photographic evidence and from the diagrams in Thiel's first patent that the movable plunger never really leaves the structure. So here at bottom dead center of our crank, we can see that the plunger is essentially at the bottom of the structure. And here at top dead center of the crank, we can see that the plunger is essentially at the top of the structure. so that the plunger basically moves within the structure and it stays within the structure at all times. And this keeps the physical side forces and other things at a minimum so that a relatively low friction sliding movement can be generated in here. So what we want to see here is that the situation is designed so that the coil would be turned on when the plunger is halfway through its movement, and because at that point we can apply the greatest tangential force to our rotating member. And to do that, we need the magnetic circuit to be already in its condition where the least air gap exists between the moving member and the non-moving member, and that the moving member can move in such a way that it produces an even more advantageous magnetic circuit as it moves forward along its path. So these are the fundamental conditions which allow the magnepulsion engine to produce tremendous amounts of mechanical energy for the electricity applied. Now, let me give you just a quick example of what I'm talking about here. We saw in the commutator circuit that his contact, the magnetic field would collapse again, and that electric pulse could be recovered. So it's important to see over here in the full extension drawing here that this is where the solenoid is trying to get to. We know that if you take any kind of movable piece of iron and put it in a coil, it will always try and center in the coil. And this is true whether there's a keeper there or not. And you can run as many experiments as you want, but the fact is that the keeper, or the movable piece, will try and center itself within the coil. So when we turn it on here, it's trying to get to this position. And it will, if we just left the coil on, it would rise to the top and stay there. So this is the basic secret. This is the fundamental design of Thiel's system, and my reproduction of it, my reconstruction of it. But even if this wasn't the exact design that he used, his design fulfilled these requirements, and therefore it is essentially the same. So now we can put all the pieces together and come up with what I'm calling here for this purpose the Lindemann solenoid engine, because this has features in it which I derived from a number of different sources. First of all, we see that we have this basic structure and we have a crankshaft, but that this, when it turns on, it is the magnetic field's already made, so we can expect that this solenoid is going to give us the biggest bang for our buck when it comes to producing mechanical energy. We have a very simple circuit here, and that this is the run battery, and it goes through the coil and a single transistor, and then back to that battery. And then we can control when it is on using a commutator arrangement, and this commutator could be a brush, or it could be a magnetic reed, or it could be an opto-isolator with a shutter, or anything like that, and or a P device of some sort that was controlled by something else. And then we just have a voltage bridge, two resistors here that put a little bit of positive energy on when we want to, and when this shuts off, then this is just a connection back to the negative. So this would clamp the transistor off very rapidly when the commutator went off. So now if we simply apply electric energy in this quadrant here, so we can pull up here, and then we discharge electric energy in this quadrant here, so the magnetic field is rising and collapsing, and we can use the entire magnetic field to cause our attraction process, because it doesn't matter whether it's delivering current or whether it's running on current. The magnetic field is there and the ampere turns are there, and so we can power this motor now not only from the energy that is coming from our run battery, but also it can run on the energy that we are returning to the second battery, because the field is the field, and the field is causing a mechanical attraction process which doesn't really alter the electrical processes much at all. So here is a very, very high COP, zero back EMF electric motor. So learning from Bob Thiel's success, we can now take the idea to its full manifestation of a rotary design and get back to a true motor instead of running it like a piston engine. So here's what I call the Lindemann rotary attraction motor featuring the S rotor. And let me just zoom in a little bit and so we can get a closer view of the structure. Basically, we're using the same circuit as we were with the solenoid engine in the last slide. But now we've replaced the piston and crank mechanism with this. And this basically is just a single coil with a C type of core and what I'm calling the S rotor. And the S rotor is just made out of iron. It could be cast iron or Selectron laminations. Anything that will magnetize to a high degree but then let go of its magnetic field completely when the impressing field is gone. And so what we see is, like the extensions coming down into Bob Thiel's solenoid design, what we have is basically an iron beam here, and we know that if that's all that was there, if we turned this coil on, this would want to rotate around and come in line with this. But now what we do is we put two arcing extensions onto that, and we make it thinner and thinner and thinner out to the edge. And the reason we do that is what we want to do is we want to produce two effects. The first is that we want to give the magnetic field a path through iron 100% of the time. So for instance, if we turn the coil on right here, there's only these two small air gaps right here, so the magnetic field in the iron or in the movable piece can be maximized. Secondly, what we want to do is we want to make sure that the magnetic force creates a tangential force on our moving member, and here again, as long as we sweep these way out to the end, we can get a very strong tangential force when the coil comes on. And of course what it's going to want to do is, as the magnetic field is established in here, it's going to want to create what's called an attraction action, and that means that the lines of force are going to want to get shorter. That's what attraction is. Attraction is the lines of force between two poles getting shorter. So the lines of force in this situation, they're 100% in iron, but they can get shorter, and they can get shorter by rotating this beam around until this member here is straight across here. That would be the shortest path. So it's going to do that, and it's going to do that with extremely strong forces, and they're applied to our rotor in this case in a completely uniform way, so that all of the forces are balanced on the beam, on the bearing system, and on the shaft. All of the forces are evenly distributed, so that the only real weakness here is that, of course, when this thing comes on, it's going to want to just bend these arms outward. So that's basically the only weakness in the design, and of course that can be mechanically restrained. So that's the one small concession we make to this situation. And so what we're going to do is we're going to, let me just widen up this shot again. So what we're going to do is we're going to turn the magnet on in this position, and then we're going to allow the rotor to rotate approximately 45 degrees until this beam is approximately in this position. And then we're going to turn the power off. So we let the magnetic field rise in strength to that point, and at that point we let the magnetic field discharge. And again, we have the same run battery through the coil, back through just a single on-off switch, back to the battery. And now our commutator can have 2 on strokes per cycle, or per revolution, because we have a situation where the rotor is symmetrical in 180 degrees, and therefore we can, every time we go around 1/2 of a revolution, we're basically in the same position, so we can do it again. So when the coil discharges, of course, it discharges back to recharge this battery. But essentially now what we've done is we have accomplished everything that we had hoped we could accomplish when we looked at the back EMF problems in our initial traction motor. And that is that the electricity event is happening here in the coil, so that when we put the electricity into here, that's happening here in the coil, and when we get the electricity back out, that's happening here in the coil. Meantime, over here is where the mechanical energy is produced, so now we have created a physical separation so that the mechanical energy is being produced in a different member by a different process than the electric induction. In other words, this is just being attracted by this field when it is present. And that field is present as long as there are ampere turns. In other words, as long as there's amps moving in this coil, there's a field here. And so we can get, if we put in power to this point, so the inductance of the coil here will cause a current ramp that will have some duration. And let's say it's 3 milliseconds until we can, when we apply at this voltage, until the magnetic field strength is approaching our optimum point. At that point, we can shut the transistor off, and because of the inductance and because this battery is essentially similar to this battery, then this will discharge in a similar time frame. So let's say this charges up in 3 milliseconds, and it will probably discharge in about 2.5 milliseconds. So now we have a magnetic field here. There are ampere turns in this coil for a total of 5.5 milliseconds. So that is the period during which we can get an attraction cycle and convert that to mechanical energy. We can see that now we are producing mechanical energy strictly by the action of the magnetic field, and so that's indirectly in relationship to the electrical input. So again, we've created a more of a separation between these two events. We've made them happen in different components using different processes at different times. So here we have finally realized our hope that we saw hidden within the traction motor or the induction motor at the beginning of this movie. And so this solves the fundamental problems of the electric motor. We can produce tremendous amount of mechanical energy here. It is only indirectly related to the amount of energy that we put into it. When we load this, it will slow down. But what we can do is, if we can design this, we can impedance match all of these things so that, let's say, we want to run our loads, let's say, at 3,600 RPM. What we can do is, we can set up the rise time of the inductor and everything so that it matches that speed point. In other words, so that we get to our maximum point here and collapse when the rotor is turning at that speed. So when it speeds up to a higher speed than that, what will happen is that it'll start cutting off before it gets fully magnetized. And so then this will, so as it speeds up from this point, it'll start drawing less and less power, like an ordinary motor. And then you can, when you put a load on it, it will start magnetizing to a higher and higher and higher and higher degree until it gets to this maximum benefit point. So it will rise, the magnetic or the mechanical energy creation will rise into the load as it slows down to meet this perfect point, at which point it can deliver power at its maximum rated speed. And so all of these things can be engineered into it so that it will have similar characteristics to a normal motor, but still run on these principles. So here we have a situation where we can put a certain amount of energy in, probably get at least 85% of the electricity back out, and we can create motor torque on both what we put in and what we get back. So this is the secret of the electric motor of the future, and there's only a few other things I'd like to show you at this time. So let's do a quick COP analysis of our new motor topology. If we assume, in system assumptions here, if we assume that our electrical recovery can be 85%, and 85% for a DC to DC converter or one of these systems is certainly achievable. Many people have built systems based on John Bedini's ideas where recovery is higher than this. So let's also assume that our mechanical energy production is approximately 70%, which basically means we can produce 70% mechanical energy from our electrical input. Now, obviously, this is all totally under unity. This is not an over-unity machine. So let's take a look at a hypothetical COP analysis. If we start with an electrical input of 100 units of energy, and we can get 85 units back, then our net electrical input here is only 15 units of energy. If our mechanical energy produced is 70% of the total magnetic field available for the attraction process, then the attraction process, the total magnetic field over here, is equal to our input and our output. So this is the total magnetic field. So we have 185 units of magnetic field energy. So if we have 185 units of magnetic field energy times our 70% efficiency, we get 129.5 units of mechanical energy produced. If we divide our output by our input here, we see that the machine is capable of producing a COP of 8.6. Now, this is starting to look good. Remember, the COPs of our permanent magnet field induction motor was 0.25. So this is something on the order of 35 times better COP than the off-the-shelf motor. Now, I was introduced to the work of Bob Thiel in 1979. By 1983, I was working in Santa Barbara with a group of people on a number of these ideas. And here are some documents from my files. This was drawn in June of 1983, but this motor was fully designed and conceived of by March of '83. And I was calling it the flux motor at the time. And you can see here in this diagram, or in this piece of paper here, the opening statement says, an electromechanical device to convert magnetism into useful work and electricity. And you can see the basic idea here. We were going to use C cores of like transformer laminations put a pulse of DC into it, attract the iron piece, and then turn the power off and get the pulse back by transformer action. And so you can see over here in the diagram to your left, we have 4 of these C-type cores. This is a top view. And the rotor had 5 sections, iron sections in it, running the full length of the C core. And these would just rotate in. So if this coil was turned on, it would very rapidly attract this iron section into alignment. So the on time here could be very short, turn on, turn off, and get the kickback. This had a mechanical brush type commutator. And so the combination of 4 coils and 5 sections on the rotor meant that there were 20 individual attraction strokes just to get the rotor around one time. And this motor was just ferociously powerful. Unfortunately, it was under development right at the time we were in the process of trying to raise money, and we were unable to raise any money. So this system was never fully developed. Here's an actual photograph of the model of the flux motor that we built in 1984. And you can see the brush commutator on the top here and the 4 coils going in towards the central member, and the rotor was deeply embedded inside here. So this is the photograph of the only working flux motor that we built at that time. This is myself and the machinist who built these amazing machines with me, Michael Knox. Here we're testing a variation on a similar 4-coil arrangement. This is set up as a variable reluctance generator, and it's powering the light bulb bank on the side from this normal type of motor. So we were working on the development of a special kind of motor driving a special kind of generator to produce a power plant. So here then we see the S rotor applied to the flux motor topology, where we have 4 of these C-type coils and cores arranged around. This is the top view, this is the side view, and so these coils can turn on and advance the rotor until it's 90 degrees past here, and then these coils can turn on and advance it the next 90 degrees, and so on. So this is becoming the beginning of an engine where the power is applied most of the time. Obviously the magnetic forces are kind of moving in pulses, but still in all the total amount of mechanical energy produced by an engine of this type is very significant. And using the circuit that I showed, or some other variation, or some other methodology, a very, very high percentage of the electrical energy can be recovered while producing tremendous amount of mechanical energy. Well, now you know. Today's electric motor holds a variety of secrets. The first big secret is the true function of the back EMF. We saw, and I carefully explained, that the back EMF is neither a reflection of the mechanical load on the motor, nor a convenient method to make the motor self-regulating. Its real function is to destroy most of the energy that the operator is forced to apply to run the motor without creating any benefit whatsoever. The back EMF in a motor is nothing more than the recognition that the direct induction electromechanical machine is always a motor and always a generator, and that these two opposite functions cannot be separated in this design topology. Its performance is not limited by the laws of physics, but rather by the behavior of the forces as they are constrained by the geometry of the design. The second big secret is that motor designs that produce no back EMF have been around for 170 years, but they've always been described as being archaic and inefficient. These designs use a single electromagnet to attract a piece of iron, and never use permanent magnets at all. In the 1970s, Bob Thiel studied this process in depth. He eventually solved each and every one of the historic design problems that limited its mechanical energy production. In the process, he built and tested the most powerful electric motors ever designed that ran on magnetic attraction. The third big secret is that electric motors run on DC pulses can be configured to return up to 90% of their input electrical energy without affecting the production of their output mechanical energy. Roger Andrews stumbled into this process in the early 1970s and successfully marketed a bunch of toys. But John Bedini independently discovered this process and after 30 years of in-depth study, perfected and patented the simple circuitry that allows this to be understood and maximized. When all of these discoveries are put together, the electric motor emerges as an astonishing machine with unparalleled power and performance. I showed you a number of my own designs that bring these ideas together. But these concepts are universal and can be applied to hundreds of design topologies. Even more exciting is the fact that electric generators can be designed to provide no-back EMF operation as well. The possibilities are without precedent. Quite simply, we're on the threshold of a new electric age. We're being told that our planet is warming up and that we must reduce the amount of CO2 released into the atmosphere. Increasing the efficiency of electric motors is one way to help. I encourage each and every one of you to experiment with these ideas. Thank you for your time and attention.